Hello, and welcome back. We're going to be doing something a little bit different today. We're going to be looking at a new array-based language called Uiua. Uiua has gotten some traction recently. I think it had it made it to the front page of Hacker News. There are people on the APL Farm Discord that are pretty enthusiastic about it, so I thought I'd take a look. Uiua combines a lot of the features of more modern array-based languages like BQN with a stack-based paradigm, which you may be familiar with if you've programmed in Forth or Joy, or I think Factor also uses this, where basically instead of um, assigning things to variables, you basically have a stack that functions consume from and put things on top of. And your job is basically to put things on the stack in the right order and manipulate them so that you get a nice sort of procession of functions to operate on your data. So we're going to be taking a look at this today. I thought it would be cool to do an Advent of Code problem. I'm going to be doing day 14 of 2019, which is one of my favorite Advent of Code problems of all time. I recently did a video about this, so you may be tired of hearing about this problem at this point. But I think that it's a good demonstration of the Uiua language for doing something of like reasonable complexity. So I won't go too much into the problem or the algorithm that we're going to use to solve it. If you're interested in a more in-depth coverage of that, you can go back and watch my favorite AOC problem of all time video. But the sort of Cliff Notes version is basically that we get a description of some reactions. These reactions produce objects and they consume other objects. And basically this fuel is kind of at the top of the hierarchy and ore is at the bottom. And the part one and part two questions basically involve like how much ore is required for various amounts of fuel. And so you sort of walk the graph and calculate how many of the intermediary components you need and how much ore that translates into. So let's take a look at Uiua. This language can be installed locally, but for today I'm going to use their online code pad, which you can check out if you want at uiua.org/pads. So go check out the coding environment and read some of the documentation if you're so inclined. Okay, so the first thing we notice is that we have multi-line strings, which is pretty nice. So we have defined a string P, which we can look at by just evaluating P. And this box down here, as we go along, is going to display the current data on the stack. Stacks work, just like the data structure does, where you can push items on the top and you can pop them off. Importantly, with this box, the way you should read it is that the most recent item added to the stack is on the bottom of this this display in this box here. So when you're reading the arguments on the stack, you should go from bottom to top. So first, we're going to want to do some parsing here, and we can put /r/in. These are the character return new line characters, which it looks like are separating our lines here. We can put that onto the stack, and then comma will duplicate the second item on the stack, and we'll put it on top. So we have kind of a sandwich here with our input, the new line characters, and then the input again. And we can do membership, which works just like membership in APL. It consumes the top two items on the stack and gives you a Boolean vector. I guess I should talk a little bit about how inputting the symbols works. So Uiua, unlike with APL or indeed BQN, doesn't use like key maps or leader keys. When I program APL, I use backtick or some other leader key to get the symbols that I want. Instead, what it does is each one of these symbols has a name, and you can type some prefix of that name, and then when you run the code, the formatter will basically replace those prefixes with the relevant symbols. So this is kind of nice because it means that you're not editor dependent at all. I mean, you could write this in Notepad, I imagine, and basically you have a formatter that's looking for changes to the files, and will do all the formatting for you as you go along. Okay, so we've done membership, and we get a Boolean vector. This Boolean vector currently has ones where all the new line characters are, so we want to do a not on that. And then we can partition. Partition works just like it does in APL, which is awesome. I'm super glad that the language creator included partition because I use it basically every problem. BQN doesn't have it. K doesn't have it either, I don't think. So it's very handy. And yeah, so now we have an array with boxes containing every line in our input. And we can drop that item from the stack just for clarity here. Next, we're going to want we want strings containing the digit and alphabetic characters, because we're going to have to parse those out. So the way that you do this is the @ symbol denotes literal characters. So we have the character 0, and then we have the number 10. So I'm putting stuff on the stack here. And then I can do range, which is just like iota in APL. And I can do plus to add these together. And this is a concept, I think this applies in BQN. I haven't done that much BQN, but the idea is basically that characters are in an affine space, which I won't pretend to completely understand, but basically means that you can add numbers to characters, and it will translate the code points. So you can get like ranges of characters and other cool stuff. So we have a string containing all of the digit characters. And if we want a string containing all of the alphabetic characters, we can do the same thing, 26 at A. And we can use a combinator to run. So basically this combines two functions into one. It's basically just a kind of a space-saving measure over parentheses. And then both will take a function and call it twice on the stack, essentially. And so we're able to run a single function on two sets of values. So we have strings denoting digits and alphabetic characters, and if we put these in squiggly brackets like this, it basically gives you an array with the items inside boxed. So we'll remove this drop, and now on the stack we have our sort of input broken up into lines and our numeric and alphabetic characters. And now we can do table, which is just like outer product in APL. And if we do both on box, and here I can get some debug output, maybe. If I drop this, it should at least give us the output. So table is doing an element-wise, is running the function here element-wise on its two arguments. We can see that we have first up on the stack is our selector, and then second on the stack is the line. So we'll duplicate that, and then we'll run membership. And once we have membership, we can do partition again. Yeah. Great. So we're partitioning everything out. And then I do reverse here. So that because the way that the the input is structured, the last item is basically special because it's the outputs. And so by reversing it and putting it in front of the list, it makes it a little bit easier to work with. And then finally, we can box it all up and we get our parsed input. If we look at the shape of this, it's 2, 9. So basically, the top row is the alphabetic identifiers. The bottom row are the digits. And then because we have 9 lines in our input, we have 9 boxes in each row. Cool. We can assign this to R, I guess. And then let's see. So we want our ingredient list. So we can take the first row of R, and that gives us the identifiers. And then we can do an each first, just to take the first element from each one. Unlike in APL, the modifiers go on the left. So everything is parsed right to left, except for modifiers, which are read left to right. And then, so these would be all of our identifiers in, all of our identifiers for all the reactions, except for OR, which doesn't have a reaction associated with it, so we can just append it on the beginning, and we'll call this I for ingredients. Okay. Then we're going to want to build a matrix, basically containing the numeric information for all of the reactions. We can do a transpose on R. This formatting is a little bit weird, but if you look maybe at the first row, you can see. Yeah, so each row contains 2 cells. On the left, we have the identifiers, and on the right, we have the digits. So for each row, we're going to want to do a reduction. And we'll do both unbox, dump ID here, so we get some debug output. So within the reduction function, basically the top of the stack is going to be our identifiers, and then the bottom of the stack is, or the second item on the stack anyway, is going to be our numeric coefficients. We're going to use a function called, or a modifier called dip, which basically takes a function and will temporarily pop an item off the stack, run the function, and then place the that top item back onto the stack. So this is a way to basically operate at lower levels of the stack and sort of get things in the right order. So these numbers here are, they're still strings, so we need to parse them. And so we can do each bind parse unbox, like so. And you can see parse, by the way, doesn't have a glyph associated with it. So, but it is a function that's included within Uiua. So yeah, we're basically unboxing each one, parsing it, and now we have numbers instead of strings. Now, we need a way to differentiate the outputs, and because of this reverse that we did up here, the outputs are actually the first element in each list. So we're going to do something a little bit tricky here. Under first negate. Under is, we don't have this in Dialog APL. I wish that we did, but it's a cool modifier that basically allows you to, you run an invertible function on some piece of data, and you change, you run some operations on whatever that function returns, and then the function is undone and everything is put back together. So you can sort of think of it almost like a lens or something in Haskell. But basically what we're doing here is we select the first item, we negate it, and then we put the list back together. And this results in our first item here being negated, which is pretty nice. Okay, so next we're going to need, because we're building a matrix, we need to have, we can start with rows of 0 of the right size. And so we can do that here. We can put 0 onto the stack, and then I, Um, and this is what our stack looks like. Remember that we're operating under dip here, so this top item is still going to be there. And we can take the length of I and then do reshape. And this, excuse me, this basically just, so we put 0 on, we put our ingredients list on, we take the length of the ingredients list, and then we use that length to reshape 0 into a vector of the appropriate size. Again, this is all very similar to what we do in APL. It's just that things are a little bit different because of the stack paradigm. So we have that. And then I'm going to put I onto the stack as well. So this is how our stack looks currently. Outside of the dip function, we can then do an index of operator. So we're going to take our ingredients list and find the indices of our identifiers. There we go. And so now we have everything that we need in order to build our row in the matrix. We have the indices where the values should go. We have our sort of blank row that we're starting with, and we have the numerical values that we want to put into the row at those indices. And so we're going to do something, again, a little bit tricky here. And this is under select gap ID. And okay, so this under, again, works just like this under first transformation that we did here. We're selecting certain values, and we run some function on those values, and then the list gets put back together with everything else unchanged. And here, I'll do dump ID here so we can get some debug information about the stack. So basically, select is going to consume these two arguments on the top of the stack, and it's going to return the selected values, which are going to be zeros. And what gap does is it basically says, I don't care about those zeros, or I don't care about the first item on the stack. And instead, so discard that, and then identity just returns the numeric values that we parsed and puts those into this whole transformation. Basically puts these values into the vector at those indices. Cool. So we get a matrix, which is nice. However, the shape of this is not square, it's 910, and that's because we don't have a row corresponding to or. So we can denote or by basically just having like a -1 and zeros for everything else because it's just a placeholder. However, if we do this, we get an error, and that's because we can't just join, a -1 on the top. Uiua has this cool modifier called fill, though, which basically says if you run into these sort of shape mismatch errors, just pad whatever element you want to make it work. And so on the top row, this basically corresponds to or. And again, this is just a placeholder reaction. It takes no inputs and just has like a single output that doesn't really matter. Cool, but we will call this M. So now we have a matrix. Next, we're going to want to write a function to basically pull out the fuel row, do the calculations and everything to figure out how much ore is being used. So I'm going to load some stuff on the stack here. We'll do fuel, ingredients, and our matrix. So fuel, ingredients, matrix. First, we're going to box fuel. And then we're going to take the index of that fuel within our ingredients list. So that looks like 3. And then we can use select to get the relevant row in the matrix. So this is our fuel reaction. And then we're going to run a function here on it. For right now, we're just going to do a repeat of 1. Repeat is a lot like the star operator or in APL, except that whereas in APL you can either pass a constant to tell it to run the function a number of times, or or a function that will compare previous and next iterations. Here, you only have the option to pass a constant. So we repeat a function a number of times. We just put ID here for now. But I'll show you a little bit later how we can use repeat to basically do the power match combo that we use in APL so much. Okay, so within this function, we're going to want to do we're going to want to drop the first element because the first element corresponds to OR and we don't care about it. So we're going to join a 0, right? This could also be, you could also do like under first, sort of the same trick that we did over here, but this works just fine as well. And then we're going to do max 0 to get rid of negative values, which are essentially surpluses in this vector. And we just want to focus on the positive values. So each one of these positive values indicate a number of components that we need. So next we can look at our matrix M, and if we do a min reduce for each row, this gives us a bunch of negative numbers. These denote how much output each reaction gives you when you run it once. We can negate all of those, and then we can do a divide. And so the idea is that we need a certain amount of components for each reaction, and if we do a division by the amount of components that the reaction gives you when you run once, this, if you round it up, will tell you how many times you need to run the reaction in total to get the components that you need. Now, this can be multiplied with M, because unlike APL, Uiua has what's called leading axis agreements. So as long as the first parts of the shape are match for two arrays that you're trying to do some sort of dyadic operation on, it won't give you like a rank error or whatever. So you can just multiply these. It makes it very nice to do what, for example, what we're doing here, which is basically a vector matrix multiplication. And then if we add all of those rows up, these are basically the outputs for all of the reactions that we run. So you can see we have new positive numbers, which means that we have new sort of needs, and then all the negative numbers are sort of the outputs from the reaction. Now we want to add this to our initial input. And so way back at the beginning, we can do a duplicate there so that we have it available on the stack. And now we can do a plus to add those together, right? So this is running the reaction once. We can run it, 2 times. We can run it 3 times. Oh, but you see, as we start running it more and more times, the output doesn't change. And so what we'd really like is to do the sort of power match operation that we know and love from APL. And so what we can do is we can duplicate the input again so that we have it available on the stack so that we're able to compare our sort of calculated output with the input. And what I'm going to do here is I'm going to use another combinator called fork. So we're going to do fork match and ID. And fork basically runs 2 functions on the same set of values. And so match will compare our calculated output and our input into the function. And then ID will just give us our calculated output. ID basically just returns the top item of the stack. And so you can see here we have a 0 because they don't match. And we have our initial or our calculated output here, right? Okay, so we can make use of this comparison by repeating an infinite number of times with a break function if this argument evaluates to 1. And this is basically equivalent to power match. I'll show you some debug outputs so you can see what's going on. So, so initially, this is, oh, maybe I'll put this over here. So this is our output. They don't match. This is our output on the second run, doesn't match. This output is the same as when we ran it last time, and so it does match. And so break will consume this and basically say, okay, this evaluated it true. I need to break out of this whatever loop I'm in. And the cool thing about break is you can use it in, I think, reduce or fold or a number of other sort of iterative modifiers. So it's pretty neat. Cool. And then we just take first to get the amount of ore. So this is the amount of ore required for one fuel. If we want to change this into a function, we can basically multiply our fuel row, and then we can assign this to f. There's our function. And if we run f1, then now this is how much ore is required for a single unit of fuel. Cool. For part 2, it's a little more complicated. We'll do rep11. Part 2, just for some clarity, basically says like, okay, we have 1 trillion units of ore. How much fuel can we make from it? So it's sort of it's kind of an inversion of the problem of finding how much ore for a single unit of fuel. And so basically what you can do is we'll do 1e12 comma. So we basically set up our stack with 1e12 sandwiched by our inputs. We run f on the inputs. We divide to see, how many times we can, or how much fuel we could get for that particular amount. And then we can multiply and floor it. And now if we run this twice, 3 times, 4 times, you can see that it converges. So again, we're gonna do the break format ID, like so. And this basically does a power match. So that's part 2. We can get part 1 back on the stack by just putting it there, and then we can join the 2 of them to get our part 1 and part 2 answers. So for this particular sample input, 13,312, which is what we got back, and then the 13,312 returns 828,92753, which is our 2 outputs here. So yeah, that is, I'll zoom out a little bit so we can see the whole thing. That is the whole solution for 2019 day 14. Again, you can go back and look at my previous video if you want a more in-depth coverage of the algorithm used here to solve the problem. Mostly I just wanted to showcase Uiua and sort of the stack-based method of solving these type of problems. I think it's super interesting. I appreciate that it has a lot of the modern sort of array-based features that I wish APL had, like leading access agreements and things like that. I'm not. I think the stack-based thing and being, basically forcing you to be tacit all the thing, I think is a little bit of a trade-off. For shorter stuff, I imagine it's much more concise. But if you have a function that, like, let's say that you have a function where you need to use the input like 6 times or something like that, I would imagine that like basically you have to each time that you want to use the input, you have to duplicate at the end of the function to make sure that it's on the stack. So it's certainly it's a neat way of thinking about these type of problems and operating. This language, by the way, is under active development. You can see that it's not yet stable. The creator basically put out like 2 updates over the weekend. He's like very actively working on it. So I advise you to check it out, and you can go support the developer too if that's something you feel like doing. Cool. Well, I hope you found this enjoyable. Yeah, this is a language that I'm checking out. I might do one or two other videos. But thanks for tuning in.